Now that we've gone through the sample introduction and GC separation side of the instrument, let's move through troubleshooting on detection and specifically the mass spectrometer with a focus on detector sensitivity. If using the mass spec, one of the most important and first questions should always be, is the system leak-free? If not, then where is it leaking and by how much? If it's a leak of any size at the mass spec analyzer door, then you need to vent. If it's a small leak and it's at the MS transfer line, let's make sure our column was installed correctly. Columns left at high temperatures for long periods of time can become brittle, and sometimes the column can break when trying to remove it from the transfer line. If you feel resistance when trying to install a new column into the transfer line, you need to take a look and check that transfer line. It shouldn't be difficult to install your new column. So what's the worst that could happen with fused silica pieces in my transfer line or my mass spec chamber? Well, the broken column could get into the mass spec chamber, which is not ideal, or it could even get into the turbo pump, and that would ultimately break the turbo pump, which is not a quick and easy nor cheap replacement. To prevent this, inspect the column when you're removing it from the transfer line and verify that it looks to be about 17 centimeters long. If it looks a lot shorter, then either use some compressed air or thin wire or an old thin piece of fused silica to push from the mass spec side of the transfer line back into the GC oven. A piece of fused silica that falls into the oven is a lot easier for us to remove and handle than one that drops into the mass spec chamber. Since I mentioned column length in the mass spec transfer line, you may be wondering if that column length extending into the mass spec really matters that much. Installation of the column into the mass spec should leave the end of the column either flush with the end of the ceramic tip or 1 to 2 millimeters beyond the end of the transfer line for most Agilent mass spectrometers, like is shown in the center of the slide. And this applies to our 5977 inert plus or extractor or inert sources, along with our legacy 5975 mass spec systems. Now, what happens if you install the column too far into the mass spec? You can have problems with detector sensitivity and loss of sensitivity, and you can also fail tuning, because the gas flow can overwhelm the source and not all of your ionolites will be efficiently ionized. Comparatively, if the column is installed too short of a distance, your tunes will pass, but some peaks may begin to tail and lose response. For example, a colleague of ours ran a test where they only inserted the column 11.6 centimeters into the transfer line. That's just over 50 millimeters too short, and then compared it to the normal installation depth, resulting in the chromatogram overlay we see here. So we can see that the peaks in blue, where the transfer line was way too short, have some shorter and tailing peaks, and they tail a lot more than our pink colored chromatogram, which was where we had a normal installation depth. We have a tool that can make column installation into your inlet or detector much easier. One complaint we would always receive is that it can be hard to keep the column length above the ferrule at the right position when you install a new column. What if the column moved during installation and then the depth is too long or too short, or sometimes I've seen columns fall out the bottom of the nut. I've seen some people use a septum below the bottom of the nut to hold it in place, but it's not a great idea since it can create another thermal zone in the path length of the column. So we developed the self-tightening column nut a while ago, which makes column installation much easier, as you don't need any tools, and you can use the same graphite Vespel ferrules on the mass spec and the inlet or other detectors. And since there's a spring-driven piston design, it continually presses against the ferrule, so you don't have to retighten it after thermal cycling. But customers still asked about how they can best hold the column in place during installation. And we made an adjustment to our self-tightening nut by adding a collar. This collar can be tightened to hold the column in place and then easily removed after column installation. With the addition of the collar, you can easily set the depth of the column for the inlet or detector, tighten that collar into place, install your column into your inlet or detector, and then remove the collar and your system is ready to run. For the mass spec, this means a new column installation allows you to quickly install into the mass spec without opening the side analyzer door and risking leaks at that O-ring. You no longer have to have one arm in the mass spec and the other in the oven trying to thread the column to the right depth. Now that we have the correct column installation depth into the mass spec, let's make sure the correct ferrules are being used. So the ferrules on the mass spec transfer line should be graphite Vespel. Graphite is not good for the mass spec since it can flake off and fracture, so only use graphite Vespel, and those are used best with our self-tightening collared nuts. Second question, what direction should the ferrule be facing on the mass spec transfer line? Should the cone, or you could call it the bell face, should that be facing the mass spec, or should the flat edge of the ferrule be facing the mass spec? Flat edge faces the mass spec. Remember that the mass spec transfer line is flat, therefore you should match flat to flat, flat side of the ferrule to flat end of the mass spec transfer line. If the cone end is facing the mass spec, the system will have a leak that just won't go away no matter how much you over tighten the nut. And remember, don't use a wrench on that self-tightening nut. It is only meant to be installed by hand. So now that our system is leak-free, are we able to perform an auto tune? The answer is yes. Do a quick check and verify that the source and quad temperatures and also your carrier gas flow rate are the same in the tune file as the method you plan to run. Does it really matter? Yes. A mismatch of your carrier gas flow rate or the mass spec temperatures can cause a loss in sensitivity, and potentially in some cases you'll see some peak tailing. If the auto tune seems to be having issues tuning, let's make sure the source is up to temp before you tune. Remember, when you're restarting a system, you don't instantly go from room temperature to 250 or 300 degrees Celsius in that source. Let it have time to reach the set temperature. Or does the tune scan show a large number of ions, say 600 or more? Then you may want to ask if that source has been cleaned recently. And it may also be time to check the source and filaments. For cleaning the source, we have a few tips. First, you must disassemble the source. You cannot clean the filaments, gold screws, ceramics, polyamide parts, or the heater block. That's a no-go. Only clean the metallic parts of the source that are shown here. For cleaning these parts, gently clean them. Throw out that green paper, it's way too abrasive. Use cotton swabs and a slurry of the alumina powder in distilled or deionized water, and only scrub very gently. You don't have to use that much force to clean up the lenses. We don't want to scratch it because that can impact performance. Make sure you rinse with a lot of water after you're done cleaning those parts to remove any particulate. And then you will sonicate in a 4-step process through water, methanol, acetone, and finally hexane. And then once the sonication in the solvents are done, allow the parts to completely dry before reassembling the source. But do you get tired of cleaning your source manually? You may clean it every month, possibly more often, and you've maybe completed sample prep and used backflush, but you still need to clean the source once a month. We realize that can get really exhausting and so time-consuming. For some applications, increasing the temperature of your source can add some benefit, but another option is using jet clean. It's not a new type of source, it's a way to keep your source cleaner longer. How does jet clean work? A low flow of hydrogen is introduced directly to the source, either during or after the analysis, to keep the source clean from run to run and day to day. Here's an example of how it works. We're going to use a red Sharpie to simulate the buildup on one of our lenses in the source. On the left, you can see what will be accomplished by baking out the source. And while the red lines are a bit fainter, not much of a difference has been made. On the right, you can see the improvement that just one jet clean cycle can make. Much of the heavy contamination has been removed from where it was exposed to hydrogen, and the remaining inked areas are consistent with what's masked in the assembly. How much could jet clean help in maintaining your instrument uptime and productivity? Let's look at what happens when a dirty sample, in this case a set of food matrices, specifically apple, is prepared using our Catcher's extraction technique. Catcher's is a great sample prep technique to clean up some samples, but even with using this sample prep method, this GC-MS-MS system still needed to be cleaned once a month, as we can see on the left side. Their standard system, they had to clean it August, September, October, once a month all the way through January. So the time to vent the system, clean the source, and have the GC-MS-MS system ready to run can cost a whole day of lost sample analysis time. Comparatively, those same samples were prepared and run on a mass spec system using jet clean in the clean-only mode, and that was able to run from August 18th till January 14th, which was an 80% reduction in their need for manual cleaning. We cleaned our source, but did you remember to look at those filaments? Anytime the mass spec is open for maintenance, it's a good habit to look at the filaments. Looking at the total ion chromatogram shown here, you can see a normal run, and that baseline is shown in pink. It looks nice and pretty flat with some peaks in it, but our black trace doesn't look quite normal. We see odd increases in the baseline, and I call it jittery with those random looking increases and decreases. And this is a scan run, it's not sim, so we wouldn't expect jumps anywhere. So those increases and decreases in the baseline tell me that it's not normal and something's going on. So a jittery baseline like this one on the GCMS could indicate issues with a filament. So be sure to run a tune evaluation, because when I ran it, my tune evaluation failed. So I knew there was something wrong with my source when I had a failed tune evaluation. So I vented the system, removed the source, and saw filament 1, which is shown on the right. The filament turns were starting to uncurl, and this was causing those odd baseline artifacts. Now, this doesn't happen on every single filament or every single run, and not every filament fails this way. But if you see it and your tune evaluation fails, be sure to check on those filaments. Today we discussed how to troubleshoot through chromatographic and instrument problems like an Agilent scientist. We compare what a working system looks like to our problems, and then we start to split up the problem between sample introduction, separation in the GC, and detection in the mass spec. But first, we check the exterior and easier locations before jumping to column replacement. So we'll look at that syringe or the vials, and then systematically move through the instrument from inlet to detector. We've also blended in some discussion on future-proofing your instrument from chromatographic problems, and also how we can decrease maintenance and downtime. Starting with taking your time on installation to make sure the liner, gold seal, septa, and ferrules, and nuts as well, are all installed correctly. Slowing down when making connections at the inlet, detector, and CFT devices, and verifying you're using the right ferrules for the column size and interface. Just a reminder, graphite Vespel ferrules for a mass spec transfer line and gold flexible metal ferrules for your CFT connections can save you a world of problems later. Ultra-inert supplies can help in the chromatographic resolution and also can lead to more ideal peak shapes for tricky analytes, such as pentachlorophenol. Backflush can help decrease the number and frequency of column trims in source cleaning when running dirty samples. Retention time locking also saves time for an analyst, so you won't have to change the quant method retention times when the column is trimmed more and more. Manual source cleaning, which needs to take forever to complete, reassemble, and then pump the system back to normal, can occur less often when using JetClean. It's an opportunity for the GCMS to do routine cleaning so you don't have to. And with that, we've troubleshot and future-proofed our GCMS like an Agilent scientist. Thank you.